是跨牌，所以我们现在是有牌，我们是有内政部登记的，有名有姓的啊，那叫中华民国计算力学学会，叫台湾计算力学学会，但是太多学会了，我今天自己是出成台湾计算力学学会啊，那简称 ACMP， 那这个也是在国际登记的一个学会，那我们也登记10几年了啊，所以我们现在国内国外都有正式营业。那今天是非常高兴哈，因为这是 ACMP 挂牌以后第一个活动，我要特别强调一下，这是第一个活动哈，我们所有的这个学会第一次的活动就是今天这一场。那为什么是今天办第一场？其实就是为了这一场，就是那我稍微说明一下为什么这个 JS 跟 ACMP 的重要性哈。我们过去要用台湾的名义加入国际组织是非常困难啊！我同学或是老师们经过这段，你们知道，要用台湾的名义进到一个学会，进到一个国际的组织，就是困难重重啊！我们需要很多人的帮忙。那这一次就是在大力帮我们，让台湾有机会进到国际计算力学学会的一个非常重要的推手啊！那我们从2015年。我们虽然还没挂牌啊，但是我们就持续办年度的活动，年度的这个conference， 算是国际会议啊。那我们第一次的国际会议的第一个 keynote 就是这次，所以这个每次第一次我们都来找这一次来赞美，这个学会才会长长久久越走越稳啊。所以actually is William Fager professors， 对 William Fager。你应该知道啊，你如果学过硕力，你就知道了啊。这个 Craig honor for his name， 就好像是牛顿的老师啊，牛顿讲座，你看啊 ，Craig 讲座教授，这个不容易的啊。Professor Chen has been involved in many activities in computational mechanics and recent research in machine learning, also lead computational mechanics to a new direction. And today is we're going to hear this to talk about his vision and his text in this very important direction. And let's welcome Professor Chen.
Maybe we can bring in AI and hopefully we can discover something that we have not been able to do before. And I also have to acknowledge all this work was actually done by my former students here. In fact, so Chen is also from NTU. He's now a very popular associate professor. Everybody wanted to work with him. He's now doing experimental work, and he has a lot of data, and he's really fantastic. Also, my former student is assistant professor, and my current student. Okay, so to get to the topic, right? What we know, science has 3 pillars, right? Theory. And everything starts with observations. It's all about observations. And of course, we all make models. We make hypotheses. And we do that almost every day these days. Well, this one is the theory. Okay? And then, of course, you have to verify the theory. That's why you do experimentation. And that's why you do simulation. Well, I would have to say maybe before 1970s, there's only 2 pillars, theory and experimental work. At that time, people don't trust computation. But now, I think computation comfortably become the 3rd pillar. Well, maybe it's time to add the 4th pillar, right? So let's see. And then, well, the objective of all the science field, it's all about doing prediction. If the science does not lead to prediction, then it's really not very meaningful. And to do prediction, then you do theory, experimentation, and simulation. So where are we now? Well, every time when we model a problem, of course you start with the most important, either physics or chemistry or mechanics or biology for the problem. You first make your decision on that. And then you construct the mathematical models. Okay? Some of the mathematical models are reliable, but some are not. Okay, so even Newton's law works only up to a certain length scale. Below that also doesn't work, right? And you know quantum mechanics, and everything now becomes statistical. But anyway, this is how we usually do things. And then once you have mathematical models, then you do simulation. Well, so here this is where many of us are working on this side, developing effective numerical methods to solve mathematical equations that are the models of certain physical problems. Well, and then you use computer to do the simulation. Well, but in the end, you always have to ask two questions. Are we solving the equations right? And that's verification, and that's this. Right? When we develop numerical methods, we always either develop mathematical error bounds, you assess how fast the solution converges. Well, first of all, does the solution converge? And then how fast it converges. So that's one type of verification. But the other type of verification, if the problems are too complicated, then you do experiment. But anyway, we do this. And I will say that after finite element method has been developed over 50, 60 years ago, actually 1950s. That's the beginning of finite elements. And until now, there are many different classes of simulation methods, such as Meshfree methods that are actually more recent advancement. We most of the time, I think we do a reasonable job here. And so I think this is most of the time okay. But the next question is, are we solving the right equations? Okay. That comes to this. This may or may not be the case. And I would say, actually, because every time if I do a simulation and people verify the solution, if there's no analytical solution, then the only way you can compare is to experimental results. If the disagreement is there, people always blame on computation, right? It's, your numerical model is no good. But I always blame on the material models. Because just think about plasticity, how complicated it is. And to model concrete, to model soil. Those mathematical models are just way below our expectation. Okay, I think I can say this comfortably, and I think a lot of you work on geomaterials and even biomaterials, same thing, right? So this is question. We be able to add the fourth pillar now, and advance where we are right now to the next level. Okay, and so anytime you do simulation, you will always have to consider errors. Where are the errors? Where errors came from? Data, number one. Right? There are noise, there are outliers. And the data, either you use the data to fit some constants in your mathematical model, or you use some data to do verification of your simulation results. Just always keep in mind there are noise and outliers. And also, data lives in extremely high dimensionality. And that the data search could also be an issue. Models, right? Of course, all these, we talk about that. Material models. There's a lot of issues. Of course, numerical methods, and we apply mathematicians and engineers to a lot of this, develop algorithms in which we prove component stability and convergence, and of course, any discretization you do is always an error. Right? So there are errors from discretization. There are errors from the numerical algorithms and so on. Okay, so here, I just wanted to say that even with the, I would say, more advanced computational methods that we have these days, for example, being able now, so this is a standard problem, not a standard, but it's a sort of a benchmark problem that we did for the U.S. Army. Is this multi-body penetration problem, and so this is the main structure. This is called a witness plate, and the witness plate will they collect all the debris fragmented from the main structure, and this is where they use this to compare to experimental data. Okay. Now, so if you look at how these are, these problems modeled, of course we have computational methods, in this case reproducing kernel particle. But then that method uses a lot of different models, plasticity and damage models. I don't know what's going on. It doesn't advance. Yeah. Okay, thanks. And then it uses some contact algorithms. It also uses some, because the solution is a combination of smooth and rough solutions. And all these two, if there's a disagreement with the experiment, that's where the major source of error. This is another example. This is so-called explosive welding. This is a solid state welding process, very different from the other welding process, where usually you put lasers, very high energy, focused energy, and then onto the one piece of metal. You melt the metal, it goes through the phase change, and then material got crystallized and then get back to solid state. So usually the material welded in between the two pieces of metals are weaker than the parent material. This is the only manufacturing process certified by NASA JPL to make the kind of containers that you can collect samples from the other planets, like collect samples from Moon, collect samples from Mars. That kind of container has to be very, very reliable. You don't want any leakage. You don't want any contaminations. Right? So this is so-called a solid state manufacturing process. But anyway, the point is that in order to form a good bonding between the two, pieces of metals, the impact angle and the impact velocity is very crucial. So instead of doing all kinds of experimentation, you can do simulation. These are called the jets, right? The solid material now forms the jet, and this comes from the large plastic flow. But anyway, my point is the accuracy of this simulation also largely affected by plasticity model and damage model. And again, contact. Equation of state, that's another major source of error. A lot of equations of states don't really work well when you try to generalize it to different, shock wave, explosive types of, hydrodynamics type of situation, and involve modern physics. And in fact, under very high velocity impact, the crystalline structures of the material is undergoing refinements, and that also affects the material properties. So it's just an example of demonstrating potential errors from the current state of the art. This is for civil engineering applications, right? Next slide. So this one, of course, is a hydromechanical coupling problem. There are also models for that, and so on and so forth. But anyway, whenever you see that now there's still slight difference between experimental observation and computation, then you start to think, well, maybe something right here can be proved. Okay, so now we come to the main topic of today's presentation. If a lot of errors actually came from material models, is it possible to avoid using predefined mathematical forms to relate stress to strength in any of the material? So here, I'm going to introduce manifold learning based on locally convex data treatment computation. Well, all these stress and strain data lives in extremely high dimension. In fact, every data point has 12 dimensions, even for isotropic material. And so searching data in such a high dimension could also lead to sometimes stability issues, sometimes the outliers and the noise makes the data search very complicated. Okay, another more recent approach that we're working on this area is that is it possible to entirely rely on thermodynamics? Okay, and most engineers, including us, we will do conservation laws, and we use it all the time. And that's the thermodynamics first law. But quite rare, we consider the thermodynamics second law. And I used to say that engineers like to solve the problem when there's an equal sign. Right? Whenever there's an inequality, most engineers don't like it. And in mathematics, there are always inequalities when you show convergence. Well, the same thing, I think when more I work on this, I feel that we should use more inequalities. Because having an equality limits your search of solution. Too limited. If you have inequalities, for example, thermodynamics, it's all about positiveness of entropy and all those things. Right? So using thermodynamics could open a door for a lot of learning the material behavior that is really hard to predict. And then I'll talk about how we can use neural network to enhance, for example, Galerkin solution for some PDEs. And then finally, as an application that we've been working on this for a couple of years, working with a team to develop a human digital twin. And we'll start with a more simplified system, but let's see how all these different techniques can be applied to digital twin applications. Okay, so let me start with very first step of data-driven computing. Often we need some physical models. Okay, and so suppose I'm modeling biological tissues. And biological tissues have a lot of different type of materials, they are all packed together. Well, I think equilibrium is something good that we all trust that. Compatibility, this is man-made. It's a definition of stress and strain. It's a definition of displacement and strain. Displacements are measurable. Displacement is a field variable. But strain is man-made. It's just one quantity to measure deformation. So, but anyway, even with this man-made quantity, you need the relationship between stress and strain. And that usually comes from some constitutive material models, right? And for biomaterial, it's way too complicated. As an example, in these muscle, biological tissues. And so, can we now simply rely on data, but assuming that we have good quality data and it's, the amount of data is sufficient, then is it possible to combine data instead of using the pre-assumed stress-strain law to do the simulation? Okay. So how do we do that? Well, let's first define what we call it physical manifold. In this case, we have equilibrium and the corresponding traction boundary conditions. We also have the compatibility and some displacement boundary conditions. So this defines this as physical manifold set. That involves, this set satisfies equilibrium and traction boundary condition. Another set that is about the prescribed displacement boundary conditions. And as I said, there's no relationship between stress and strain, so it's hard to relate stress back to the boundary displacement. Okay, so for that, let's assume that I have a rich data set. Whenever you see head on top of the notations, that means those are experimental. Right? So anything with the head are experimental measurements. So really the objective here is to search for the intersection between the physical manifold and the experimental data set. Right? So how do we formulate this under an optimization problem? Well, that's some work been done, and we follow more of these work. So he defined so-called distance function. The distance function measures the difference between, the notation doesn't come up. These are head, so different computers do. Okay. So this is the head. This is experimental stress and stress and physical stress. And this is experimental strength and physical strength. Right? So you measure them in a more of a quadratic form. So this is more in the energy type quantity. And then you want to minimize this with a set of experimental data and physical state. And you can recast this into a two-step minimization problem. First is a global step, and then the second one is called a local step. And we will solve two optimization problems iteratively until we find a physical state that intersect with the material data sets properly. Okay, so first the global step. We are minimizing this distance function now, subjected to equilibrium and traction boundary conditions. So of course you can form a Lagrangian, and that's this is the objective function we try to minimize, and then subjected to two constraints, just put a Lagrange multiplier in there. And if you look at the stationary condition, you're going to find out that these two Lagrange multipliers are related to each other. If you plug this back in, you get three sets of equations. The first set of equations allows you to compute stress from the surface structure. So you can view this as a generalized equilibrium equation. The second equation allows you to relate experimental strength, epsilon hat, to the physical strength in terms of displacement. The third equation allows you to relate the experimental stress data to the physical stress state through Lagrange multiplier. So computationally, what you can do here is you start with some experimental strength state, and then from there you solve for the displacement field. And then you look at the first equation. Anything with blue colors are given. Okay, so T bar is a given traction on the boundary. Stress data set is also given to you. And you can use these two together to compute the Lagrange multiplier here. And then once the Lagrange multiplier is computed, then you can compute the physical stress state. Okay, so that's the first global step optimization solution. Now it comes down to the local data search for given physical state solved at the global level. Now we're coming here to search for the closest data point. Now, well, first of all, I can only, in terms of plotting, the best I can do is to plot the three-dimensional figure, but every data point has 12 dimensions. Okay, but so this is just a representation that, well, the data might live in extremely high dimension, but there is usually there's an underlying low dimensional submanifold. It's for us to discover that. Okay, and people working in data science, they have been working on this for a very long time. Naturally occurring data usually reside on a lower dimensional subdomain. And there's a very nice approach. It's based on the locally linear embedding theory. And whenever I learn more from data science, I found some similarities between data science and actually numerical methods. These can be extremely high dimension. And it would be nice if I can discover entirely the low dimensional manifold. That would be nice. But if I don't, well, then you just search for the nearest neighbors. Because right now our problem is we have the physical state that has been computed from the first level optimization. From the physical state, suppose it is here, and I'm searching for the proper data set that can be sort of be consistent with the physical state. Well, I don't really need to know the entire in terms of the geometry or nonlinearities of this lower dimensional manifold. All I need to know is some a few neighborhood points, and this is almost like using localized linear function to approximate higher order true solution, right? So if you just look at the local approximation, you can do something fairly simple. So that's this, idea. What it does is really, and again, this is supposed to be a head. But anyhow, what it does is that for a given location, you first define the nearest neighbor. And then the idea here is that if you do a local averaging, and you should be able to then weighted average to represent the data, a different data but within the same group. And so if you minimize these squares in function, they'll be able to find the optimum weight that best represents the local data set. You have also the condition that you need to satisfy here is that all the weights have to sum up to 1. So again, you can relate this to partitional unity in solving any PDE with say finite elements or Meshfree method. All the approximation function has to sum up to 1. Otherwise, you can't get convergence. There's something here, but in data science, having this property is really to guarantee the invariance of the data set under translation or under rotation. So it serves for different purposes, but they all have these important properties that we need to satisfy. Okay, so then from there, what we propose to construct a local convex Hall. Right? So with this local data reconstruction and with a given physical state, I can then look into the local nearest neighbors. And I will then construct a convex Hall. And convex Hall, convexity is nice because, first of all the weights are supposed to be positive, non-negative. They all sum up to 1. So you really have this convexity property that sort of guarantees stability of this data search. Okay, so here this is what is going to give it to you. If you have some neighboring data that you identify, and then you form a local, this convex Hall, then any projection of a physical state to the convex Hall, if the physical state is within the convex Hall, then it will be just right there. If not, then what it gives you is the closest point projection onto the local convex Hall. This has significantly enhanced the data search sort of stability. In the earlier work, for example, by the group of micro-OTs, they simply look for the data point that is closest to the physical state. But that makes the algorithm, well, it's very simple, but the results are too sensitive to the noise in the data and too sensitive to the outliers of the data. Having this convex Hall, with the coercivity or convexity, it really stabilizes this whole process and it becomes more robust. Okay, so here is a test. Again, we work with Chen. He is now a very good experimentalist, and he measure do some tensile tests by actual tensile tests and pure shear tests. So there are a total of 11 protocols, and each protocol has many data that they stretch the material from small strength to large strength, and then conventional way of using this data is to fit them into some well-known material models. Right? So for example, the Tang Fan model is very famous. This is the YC Fan, Feng Yuanzhen, right? So he's the grandfather of biomechanics at UCSD. Unfortunately, he passed away a few years ago at the age very close to 100. So it was a big loss at UCSD. But anyhow, this is a well-known model. There are a few constants. So what you will do is you use all these data points and you do a regression, and then you get all these material constants, and then you use that to predict other type of deformation modes, right? And then there's another, actually it's also getting popular, is the model by Chen and Michael Sachs at UT Austin. Anyway, there are also constants, and you can characterize or fit those constants, and then use the model for prediction. So let's do a comparison of using either Tan-Fan model, where you see some deviations in compression range, this is the DSX model. You also see some deviations. And this is the model 3, entirely based on data. Well, this is not a good, not the end of the story, because the data lives in extremely high dimension. And so doing data search could be very expensive. So we further introduce this deep autoencoders. The idea is to project the high dimensional data onto the lower dimensional, so-called embedding layer. So graphically, it's almost like projecting this onto a room. And then we will then extract any features that you wish to extract, or to relate some quantity to another quantity. You can do it much easier at this lower dimensional embedded space. And it can be shown that this encoder and decoder, that means you can actually take the low dimensional data and reconstruct the data in the original high dimension. This process actually has the ability to filter the noise and to recognize the underlying data structures. The approach is also very generalizable to other types of, to do the prediction. Okay, so compared to the first method that I introduced, which is locally convex data-driven computing, every time when we have a global physical state, we search for data at the local convex hall, but in the high dimensional space. Right now, this autoencoder approach, we will now do it offline by projecting the data onto the embedding space, and then we search for the data in this much lower dimensional data space. And then, if necessary, you can then do decoding and get the data points and project them back to the high dimensional data space. Okay, so now let's look at this more challenging problem. Among the 9 test protocols, we use protocol that are with black color. So protocols 1, 7, and 8, 3, and 4 are used for training. And then we would like to now make a prediction on the solution of protocol 2 and protocol 5. Okay. And as you can see, protocol 2 is actually within the range of the data that has been collected and been used for training. So it is expected that the prediction of the material behavior in protocol 2 is easy because it's interpolated type of prediction. And you can see that both LCDD and this autoencoder, they do a good job. But if you try to then do the prediction on protocol 5, now protocol 5 is outside the range of the training data. Then the first method, LCDD, actually leads to some noticeable error. But the second approach actually is still doing a reasonable job. Okay, so now the next idea is to maybe consider thermodynamics in predicting the stress strain behavior. Hopefully, we don't need to use any predefined material law or stress strain relationship in some mathematical form. Let's see how much time I have. About 10, 11 minutes. Oh, okay, sure. Okay, fine. Okay, so thermodynamics, there's several considerations here: strain energy convexity, and rate of mechanical dissipation, framing difference, time consistency. Small strain always should be to small stress increments. And then, with the thermodynamics consistent recurrent neural network, which I'm going to introduce, all it requires is some measurable material states, for example, stress and strain, and then we can use that to train the data, and then automatically identify the internal state variables. And once the internal state variables are identified, you can compute everything else. You can compute entropy, you can compute energy dissipation, you can compute for given strain, you can compute stress. So that's the idea. Now, conventional recurrent neural network has been actually used to try to predict the path-dependent material behavior. The main idea is that every time when you try to predict, say, for a given strand, and you try to predict the stress at the next time step, you will use many information in the past, let's say, for example, 20 steps or 10 steps, and use all those history information to then try to predict what the material is going to behave in the next part step. And it has been shown that actually error accumulates from step to step. So as you have introduced more and more loading steps, the error accumulates. So this is the new approach that now we introduce thermodynamics. And what we did in this approach is we will use strength history, stress history, and if temperature is also part of the game, also temperature. For example, in the past 10 or 20 steps. But instead of using that to predict the next step behavior, we use that to identify the internal state variables. Okay, and internal is denoted as Z here. Once the internal state variables are identified, then you can then compute and you can from there you can also and all this information compute the Helmholtz free energy. From internal state variable and Helmholtz free energy, you can then compute entropy if temperature is also involved, and compute the mechanical energy dissipation, and you can also compute the stress. And you can compute anything else. Okay, so now you can now predict this kind of behavior. This is very difficult to predict, even with any of these existing plasticity models. But I think this algorithm seems to do a reasonable job. All right, now the next topic I want to talk about is it possible to use neural network to enhance, for example, finite element solution, to enhance maybe Meshfree, RKPM solution, if somebody is working on a phase field or other things. Is it possible to use a neural network as enhancement of Galerkin solution? So the problem we choose here is to model fractures. Because if the problem is simple enough, everything is smooth, I think the variable methods are good enough, and we don't really have to worry about that. But for problems with fractures, now that is still considered a very challenging problem, even until today, right? Because you don't know where the crack is going to grow. You have to do continuous mesh refinements and to capture the crack tip behavior, so on and so forth. So the proposed method is this. I don't like to do mesh refinements. I hope I don't have to do mesh refinement. I will have just sort of a background grid. Background grid will be the grid points used to construct the smooth part of a solution. And then on top of that, there will be crack, that are going to be initiated and then propagate. We will use neural network to capture those rough solutions, because rough solutions are much more difficult to predict or to represent in the conventional Galerkin type of method. Okay, so again, for the smooth part of a solution, we just use, for example, RKPM that provides a smooth solution as a background solution. And then on top of that, we now construct neural network enrichment. And here, we also don't like to use the conventional neural network because quite often you have to, especially for very complex topology, you have to use very deep neural network. That makes it also very difficult to converge. So our proposed idea is to use superposition of some shadow neural network. Each neural network, it may be just represent some very basic topological geometry of this crack patterns. And we will then rely on superposition of the lower order topological geometry to represent higher order topology. Okay. So that's the idea. So each of the neural network block contains two parts in its construction. The first part, we call it a neural network kernel. This part of the neural network would determine the localization location, and the localization orientation. And then also the solution transition through this so-called localization band. If this is a shear band, the solution across the width of this localization is entirely different from the solution across the width for cracks. Okay, even the regularity is entirely different. One is discontinuous in a strongly, and one is discontinuity in a weak way. And so they need to be represented by properly and captured by the neural network. Right? So this part of a neural network captures the location and orientation, and also solution transition through the width of localization. And then the second part of this neural network block is just some polynomial. It's just some possibility for you to enhance the accuracy of this type of solution solution construction. Okay, so just very quickly for this sub-block in searching for localization, orientation, and location, we use this hyperbolic tangent as an activation function, and we use the neural network really to identify. Probably I should just move to the next slide, because the real crack pattern can be fairly complex. But if you can find the proper parametric coordinate and map onto that parametric coordinate, they can be fairly regular. Of course, I don't expect this to be possible for very complex topological pattern of cracks, but for something that are not too complicated, this is possible. If you can then capture this, then you just rely on superposition of this lower order topological pattern to represent the higher order topological crack patterns. So that's the idea. And the rest is really. Okay, so now in terms of solution transition across the width of localization, well, the philosophy here is I don't want to just do like a brute force approach and let neural network to figure everything out. We actually construct the approximation in terms of just a few parameters. Right? So for example, if you take two subclass functions, if you work on neural network, you know this function. The derivative of that, it's the standard, the activation function. But if you multiply two subclass function, it gives you something with a localized support, right? And then you just have to introduce some parameters. At least for our case, we introduce some parameters to control the localization width, which is y1 bar and y2 bar. We also design CIs as a scaling of the width, and so that will give you the shape of solution across the localization. And then we design another parameter beta I that controls the derivative behavior of the solution. Right? So here just to show you, in the end we leave only 6 parameters: y1 bar, y2 bar that controls the localization of the bandwidth, C that controls the solution transition across localization, and beta controls the derivative of the solution across. And you can maybe introduce more, but for now, we introduce only 6 parameters. Right? But anyway, the message here is at least we found it to be not very effective just to let neural network to figure out everything. I think human knowledge is still useful, and quite often it's a combination of the two could do a really good job and more effective. So these are some conversion studies. It'll be nice. I think we can hopefully be able to get more mathematical error bounds on this approach. But for now, these are just numerical error analysis. Here we study the L2 error norm, the convergence rate of L2 error norm with respect to the number of neurons in each of the neural network block, which is about 2.2. The convergence rate with respect to the number of neural network block is about 3.6. but these are numerical. Okay, and it'll be nice that I hope this will make some mathematicians get interested to work on this. And here I'm going to show you a model of a one-dimensional localization problem. And this is the reproducing kernel. It doesn't capture any localization. And rely on neural network to capture free localizations in this form. And this is a total solution into some of this. And this just show you, different neural network block captures different localization. The first block captures the first localization. Second block captures the second localization, but also a little bit of the first localization. The third block captures the third localization, and the fourth one, in fact, captures the same localization. But it's a summation of all these represents the total solution. Okay. And just to make a comparison, if you just use a standard reproducing kernel, you need up to 800 unknowns to get a very good solution. But with this, we use only 21 reproducing kernel nodes, and I think 3 or 4 neural network blocks. Each one has 9 or 6 unknowns. Anyway, altogether 56 unknowns. So it's 56 unknowns versus 800 unknowns, and be able to obtain the similar solutions. We also use this, for example, to model more complex fracture patterns. And again, the background grid for reproducing kernel is fixed, just like this. But as the crack grows, the neural network will capture that. And this is a comparison with the experiment. How much time I have? 10 minutes or not? Okay. Okay, anyway, this is another application to use neural network to capture what's called the block dislocation. This is a double system. As you apply tension, it forms blocks of structures. Well, I wanted to spend like 10 minutes to talk about digital twins. The key difference between the digital twin model and a conventional numerical model is that digital twin has to come from as built. Okay, because that's what is meaningful. And here are just a few projects that we have worked on. This is the most current one. This is to build a digital twin for batteries, battery materials. And this is not currently funded by NREL. I think some of you are from NREL, or maybe not here, the previous group. And these are for bio applications. It's for composite materials. Anyway, I think I can skip this. Just to say that with reproducing kernel particle method, with this Meshfree method, we don't need to do geometry reconstruction. The pixel points are the model. Right? So all the pixel points in for example, MRI images, they are directly used as a discretization point. So there's no need to do geometry reconstruction, to do meshing. And it's just the pixels in the images are our model. We do need to do segmentation of materials because we need to know which part of material is what. And for that, we have, in the earlier work, we use level set. And this is the work by Tony Chen and Vest at UCLA, my former colleague at UCLA. They have proposed this multi-phase, multi-channel level set method so that you can do segmentation of, in this case, about 8 or 9 different material components in the muscle tissues. And now you can actually now use that and to identify the material boundaries. And this is another application for bone structures. Judy was the one who worked on this. That was some time ago already. Well, now let's see if we can use machine learning to do now segmentation. So now, well, I think I'll just skip this. You can use RKPM to model pixel points. And so that's it. Okay, so now machine learning. It's about decision. It's about classification of some points. Right? So this is about decision making. We can learn from support vector machines. So for example, if I have 2 set of material points, all the pixel points in the images represent different materials with different colors. So for example, this, well, you know that you can draw a straight line and you'll be able to separate them. And then you'll be also good to know the margin between the line of separation to the closest distance to the group of material and to the next group of material. Well, if you have more complex patterns like this, then it's a curve to separate them. So that makes it more difficult. But there's an approach that's called a kernel. It's called a kernel trick. That in this case, you can actually project, in this case, the two-dimensional data point to three-dimensional. Right? So this is when we want to go to high dimension. Previously, we wanted to project all the data from high dimension to low dimension space so we can do a better search, an easy search. But here, in order to be able to separate the two groups in the, just by a plane, well, you can actually project them to high dimension, right? And then once you do that, for example, with some kernels, some Gaussian functions, or other polynomial functions, then now you can just put a hyperplane in the middle, and the projection of the intersection will be the separation line. So you can now use support vector machine to define the decision boundaries, and that becomes very effective, especially once the decision boundary is determined. You can actually use support vector machine to also compute the sign distance between each of the material point to the interface, and that allows us to use that to construct approximation functions to give the proper jump conditions across the material's boundary. Okay, so I think I will skip this and show you the example. So here is one composite material image, and we use finite elements to discretize it, and it requires up to 112,000 nodes. Where we use this support vector machine coupled with RKPN, it requires about 1/10 of the discretization points, and to be able to get almost the same results, right? Simulation results. So now you can deal with this all three-dimensional images. You can construct the digital twin models directly. Okay, so now we now have a dream here is that every baby should, when a baby is born, to have a twin, have a digital twin, and the digital twin should grow with the baby. So each one of us should have a twin. That twin grow with you since you were born, and more information be added to it. And of course, you have to do, for example, a lot of patient-specific MRI and check everything. But if that can be realized, then you can actually use that to do, for example, prehabilitation and rehabilitation type of stuff. So our model, of course, you can go deeper, a smaller scale, but we start with a cellular model, and then we do detailed image-based modeling of the tissues, and then use manifold learning and reduce order modeling to pass the information from cellular scale to the continuum scale. Now, at this, component scale. At the component scale, one can also measure the muscle activation history using these wearable sensors. And then at the whole body scale, one can also put markers at every joint, and from there measure the joint motion. So now the problem statement becomes like this: if I have the patient-specific, images, and also all the, physiologically important parameters, I hope that I can use this to predict the performance of your body, right? How high you can jump, how fast you can run. You can use to train the athletes. You can also use this to train soldiers. Well, we can also solve an inverse problem, which is if I can measure the joint motion and I can measure the muscle activation functions. Hopefully, with these two information and with also all your muscle, MRI images, I can back calculate the physiologically important parameters for disease detection, for injury detection. Right? So for example, we have this classic baseball game here, right? So all the pictures are golden arms, right? They're so variable, and so the idea is, well, hopefully from the picture, if you take the camera and you put all the markers here, you can then get the joint motion in time, and if you also put the wearable sensors on in each piece of muscles, hopefully we can then predict is any injury independent or maybe there will be disease, hopefully not, but if there's any, hopefully we can detect that early on. And just wanted to say that, so this is our student. So these are the markers that measure the joint motion right here. Here have some, wearable sensors put it right here to measure the muscle contraction histories for bicep, tricep, and even pieces of muscles. Now the key, I should say, the major difficulty here is that all the muscle activation functions are with extremely high frequency. The wavelengths are so small because you measure at a very small length scale. Whereas the body motions are with much high, well, this is with a very high frequency, but the body motion is with a very low frequency. And then you try to map this to this through some physics laws. Those are, multi-body dynamics. It makes the mapping very difficult. And one approach that we took is to map the time history functions to a set of coefficients or basis functions. Right? So for example, you can use Fourier basis plus polynomials. So instead of having a time history of that, you now have a set of coefficients for this muscle activation function. And then you do the same thing for the joint motion. Also map them to a set of coefficients of sine, Fourier basis and polynomial basis. So now all you are doing here is to do the mapping between two sets of coefficients, and then also satisfying the multi-body dynamics. And that mapping is a lot easier. So this is the time history mapping with the physics informed, the multi-body dynamics. And you see that the results are very noisy, and it doesn't really agree very well with the measured, joint motion. But this one is much better. Another approach that we have introduced is to use multi-resolution to decompose the data into, using wavelet basis, project them into the coarser and coarser and coarser scale, and use the coarser scale to do the training. And then you train a model, you then transfer the training to the next final model, and the train to pass on to the next final model. So finally, that mapping at the full scale can be mapped to the joint motion in a more effective way. So I think that's pretty much what I have. I just wanted to say that I think machine learning in many aspects give us some ideas, although human designed that. But in turn, we actually can learn a lot and be actually motivated by some of the observations that we learned from this. And I think almost every field should really look into the possibility of using AI and possibly bringing new breakthroughs. And for people like me doing computational mechanics, we're looking for the possibilities of combining these two methods to come up with a new computational paradigm. Thank you very much.
I guess there are lots of contents to digest, but due to time limit, I think we only allow one or two questions, very quick. Is there anyone a quick question from the floor? Anybody? If not, I will take a privilege to ask one question. Our recent search in ChatGPT, you know that,
Right.
based on a so-called foundation model. This is a large language model. I'm just curious, is there any chance that our mechanics has so-called foundation model, so we can build on top of that?
Yeah, we just have not discovered that. But hopefully, with this kind of new technology, hopefully we can discover some unseen or underlying very fundamental rules that we have not recognized before. I think it's absolutely possible. Absolutely possible, because the data is too much for us to recognize that. And now with this machine learning techniques, I think there is a very good possibility to discover new knowledge.
Okay, well, if, I think I would better close this session because we're going to have a refreshment outside. So you can take some refreshment and chat to Jess, and this should be a wonderful opportunity for you to know him. But before we do that, let's give Jess a big hands to thank you for
So first, it's my great pleasure to speak right after Professor Chen. And today I would like to spend a very short period, like 10 minutes, to share with you guys about our recent works applying machine learning energy models to study the nanomaterial mechanics. So I know that some of you guys missed the movies at the first place, so I would like to replay this. So just to echo Professor Chen's the last topic. So this is dislocation. So this is in the molecular dynamics simulation of a dislocation gliding through a chemically complex alloy. And as you can see, this the distorted region is actually amorphous and hexagonal closed packed region. So it's chaotic. So I'm going to talk about this briefly in the later part of my talk, if I didn't use all of my time. Okay, so the first difficulty we face is that how can we, as you know, that in atomistic simulation, we need to have an interatomic energy model to describe the interaction between atoms in the system. So this is the energy partitioning scheme proposed by Bader and Marinello. So this is scheme. So start from Cartesian coordinate of atoms, so we can encode them into a rotationally and translationally invariant vectors G, and they actually look like this. So basically, we include both the pair interaction and the three-body interaction, and then we can let all this feature vector embeddings passing through all this atomic neural networks, and then this neural network looks like this, and then pass through, and we have the total energy of the whole system. So we use this scheme to train a neural network model of this FAMATBIBR, and as you can see, this is a very complicated mixed-ion perovskite. So these are done by my former student and my former postdoc, and this is very complicated material you see. So MA actually looks like this, and the FA actually looks like this. So you can see that by using neural network, we can train an energy model. So the horizontal axis shows the ground truth from VASPA calculation, and the vertical axis shows the prediction from neural network. And you can see that the parity is pretty good. And we can also have a very good parity between atomic force. And then we can, because this is much faster than the DFT calculation, and it's almost as accurate. So we can use that to do extensive sampling over the compositional space. So this is the concentration of chromium, and this is the concentration of methyl ammonium. And then we can isolate all the low energy structures and use them to compute the band gap and compare with the experiments. And then furthermore, because the neural network model is very efficient and it's very fast, and this allows us to map a lot of physical and mechanical properties of this complex perovskite, and then we can use that to build a Pearson correlation matrix, which basically allows us to figure out, to reveal the process structure and the property relationship of this complex perovskite material. So we can find the correlation between the concentration of constituents and between this structural properties like shear strength and the volumetric strength, and then finally about the property. So we can use to find out the composition regime that can potentially lead to phase segregation and the bad and the relatively poor device performance. And then the next one is that so recently we have joined work with Professor Solovitz and Professor Yang Yong at Hong Kong, and they synthesized this chemically complex alloy with a very high elastic limit. And the most interesting thing about this alloy is that when it's upon plastic deformation, it can show both the crystalline phase shown where it can have a crystalline phase and also, as you can see from here, an amorphous phase. So when it is yield, it can have both crystalline and amorphous phase. So we want to study the large scale plastic response of this material. So we use another machine learning-based energy model called the spectral neighbor analysis potential, and it is similar to the artificial neural network. So we start once again from Cartesian coordinate, and then we convert them into another set of feature vector or embeddings. Now this is called, then we're just running away. So we convert them into bispectrum components, and then once again pass through a linear summation with this very simple, or you can say it's equivalent to a one-layer neural network, and then we can obtain once again the total energy. And so this is done by my current postdoc, and this is basically the training flow. So we once again start from a large set of quantum chemistry training data, and then feed all these parameters. And once again, these are the training results. So this is the energy from mass calculation, and the energy predicted from this snap potential model. So they are in very good agreement, and this is atomic force. And with this, we can perform very large scale. So this result are from DFT calculation, and these are basically the size limits that allow us to use DFT. But using the Chen, the machine learning potential, we can do this. And this is the simulation of a compression of a nanopillar of this alloy. And you can find dislocation, nucleation, and the formation of amorphous shear band. So this is identical with the experimental observations. And once again, so this is viewing from the top. So you can see dislocation propagate through this nanopillar. And we can also stimulate dislocation dynamics. So you can see dislocation glide through and leave a bunch of defects behind. And we can also identify the core structure of a screw dislocation and edge dislocation. So it basically looks like this. And the Burgers vector, so I didn't mention that in my slide, but the Burgers vector predicted from neural network, from this snap potential is the same as that observed from experiments. And then we didn't put the dislocation, the structure with dislocation into the training set. Okay, so this is a summary of my talk. So this is the accuracy. This axis shows accuracy, and this axis shows the system size, and this shows the time allowed for simulation. So you see, so this is very small, and this is well, I think right now this one should shift a bit backward. But anyway, so for DFT calculation, you can have very high accuracy, but a very small size, and a very short simulation time. But for classical MD simulation, the accuracy is kind of doubted, and but however, you can simulate a very large system size, and if you have a very specialized machine like Anton, you can simulate a very long time. But the accuracy is a real problem. So by using machine learning energy models, we can have a very high accuracy compatible with the DFT calculations, and smaller system size, and a little bit shorter time scale comparing with classical MD simulation. So that's all I want to share today, but I still have one more last slide because my colleagues strongly asked me to show the last slide. And I'm going to speak that in Chinese. I'm sorry. Wow, that's funny. I'm sorry. I forgot. Well, because this is the file I uploaded in the morning, okay. But I changed the file a bit in the during the lunchtime. But anyway, I did my job. But can I use the 1 minute for advertisement? Okay. 我最后一张 slide 其实是那个 中研院应科中心有暑期大专生实习计划，所以欢迎各位大学部同学有兴趣的可以去申请。然后我要强调一件事，就是说，我们其实非常欢迎工学院的学生，因为大家会觉得中研院好像就觉得应该是物理、化学 whatever 嘛。可是其实呢，我们也很非常欢迎工学院的学生去参加。然后应该是明天或后天晚上，我想想看，对，明天晚上应该是明天晚上在台大有一个说明会。这样，然后很不幸，这就是他投影片里头。好，这就我今天要分享的。Thank you very much。我这个首先呢是我要强调一件事情是，我这个只是经验公式。This is just empirical, because I think at this, what machine learning potential is still more complicated in terms of format. So I don't think it can be compared with that of classical MD in terms of system size as well as simulation time. Because for classical MD simulation, once they just throw out the Lennard-Jones potential, then nobody can compete.
Sure.
Yeah.
好，那我们的。
我觉得可以再加一个轴，是有关于它的应用的拓展方面，就是今天是在这个 system 之下，那如何应用到别的 system 的时候，它可不可以承接这个部分？
你是说那个 transferability 吗？对，这个是一个很好的那个问题。不过我这张图是在脸上，一时之间找不到别的地方可以塞。
好，那我们的对，谢谢包老师。谢谢。
Good afternoon, everyone. It's my great honor to share my recent research result with you. Today, my topic is continuum mechanics of extreme response analysis and measurement noise reduction for Stokes flow, considering uncertainty. So this is my content introduction, and show the basic method for finite element method. Extreme response analysis is about the analytical continuum mechanics and the measurement noise reduction. And finally, I will share my closing remarks. So as we know, there are many uncertainties when we do the experimental the measurement. So especially for mechanical engineering, we want to measure deformation. So here I show the measurement map. So the horizontal axis is the strength view. It's about the window size, and the vertical axis is about the measurement resolution. And here the measurement is all about strength. So strength basically is the relative comparison about your reference length, right? So we need the latest grating. So this is the classical the way to think about how to develop some new measurement method. So classically, when we want to enhance the measurement accuracy, you need very fine the grating, so-called we can call the interferometry. And recently I do a lot of microfluidics experiments. So we know we do have many uncertainties. So here I come up with an idea how to quantify, how to analytically to catch the uncertainty from the source to the response. So this is the cell, the picking up experiment. When we put some like trypsin, like protein, to make a new curve for the cells. Now the cell may have some polarity. So when we turn on the electrode, and we can collect the sales we want. But somehow we may lose some the very good sale. So we need accurately describe the experimental uncertainty, or we can call the error. So I will skip any details. So usually when we write an article, we need to describe what the standard deviation about your experimental result. So I know I may get quite several questions. What the error source? What's the deviation? Why do you have this deviation? So like this control measurement, and after the cell removal, if our experimental system is robust, actually this after the removal should be identical to the original control experimental setting. But usually we cannot get identical one. So I skip many details. So I think 2 points. One is identical those extreme events. Second point is how to remove those noise. So here I pick up the easiest fluid dynamics model called Stokes flow, because this flow is linear model. It's very similar to the solid mechanics, the linear elasticity. So I adopt the wind engineering the method for predicting extreme response called load response correlation. As long as we can describe the external loading, the uncertainty, in terms of mean, standard deviation, and the pair correlation coefficient, we can analytically get the solid system extreme responses. So similarly, if we can have some linear system, here I show you the Stokes flow, because Stokes flow is linear system, so I can adopt the whole thing, the whole framework to do the extreme response prediction. Second point is, here is my former advisor. He used called experimental field projection to remove the experimental measurement error, or you can call measurement noise. Same idea, because this is the linear system. So in microfluidics, we can write down, we can describe our system in terms of the linear, you can call it elasticity matrix, and the response and the excitation. So I use finite element the model to describe the system we have. So as I mentioned, if we put the average plus or minus, here is the peak vector, because usually the experimental data we have the Gaussian distribution. So if we control 1, 2, 3, even 3.5 times the standard deviation, we can reach even the 99.96%. We can cover the whole data set. That means we can reach the extreme events. So I will skip the details, because they are all analytically. So it's very convenient for computational guys to get these numbers, because D is the stiffness matrix. So I have some result. So here is the lead-driven cavity flow. It's a very typical demonstration example. Suppose the excitation has some uncertainty. They have some uncertainty. We describe the uncertainty in terms of average, standard deviation, and the correlation coefficient. As long as we have this clue, we can analytically get the extreme response prediction. Here, many dots mean I think 10,000 sampling tests. So I think this result is quite reliable. So I just skip those results. I will move the second point, the measurement noise reduction. Okay. So because we know the signal contains the data plus noise. So our job is to make the noise managed as much as possible. So here the theory is about we just compare the measurement and the theoretical distribution, and try to minimize their discrepancy. I think constraint is important. We believe loss data distribution should follow linear elasticity. So I think this is typical procedures. You can list the quadrature and use the Lagrange multiplier. So I think here finite element framework is important because you can express your data points through the nodal variables. So here I think, as you can see, the third column is the measured data, and after the noise removal, we can get the clean the measurement field. So I show, and also we apply this technique to real experimental the data set. Here is the fly brain, and because a fly brain, if the fly has some disease, the brain may have significant deformation. I mean the brain. So, but biologists they just took image, but they cannot extract numbers, right? But like mechanician, you guys, you can get a number from the image through this we call reference net technique. Basically, we describe the mechanics theory in Euler framework instead of Lagrange, because if we describe the solid the material constituted law or equivalent equation in Euler framework, there's no gap between the surrounding fluid and the solid materials. I'm still working on this topic. Hope I can share my result with you soon. I think I might talk. I think it's up to here. Thank you very much.
Hello, everyone. It's my great honor to be here, and I would like to share how to use Model 3D to do the numerical simulation to the IC packaging process. In this slide, you can see many important names on here, and the IC packaging is around here. It's the end of fabrication and the assembly and test. From the IC design to the front end, about the schematic design, to the layout, to the for the back end and the fabrication, and there are very many famous software to deal with all the process. And for IC packaging, I think many of you here know that Multi 3D is an expert for the polymer material and polymer manufacturing. Therefore, we play a very special role here to do the IC packaging simulation. The numerical simulation can help people to predict the void when the feeding process and the warpage and the shrinkage when the phase transition and the cooling process, as well as the reliability, especially the thermal cycle fatigue. The numerical simulation can help people to do that. For conventional IC packaging process, like transfer molding, mostly using the strip level packaging, we can see the molding compound, the pillar shape inside the plunger. We compress and melt them and inject into the mold. This is the so-called transfer molding. Using the numerical simulation, we can adjust our gate position and improve our mold design. We can also predict the void and to change our vent location and try to change the flow rate and the temperature to find the optimal design. In the meantime, we can also do the computation of fluid and structure interaction to predict the copper and gold wire deformation and to prevent the wire crossover and contact. As well as we can also predict the deformation of the leaf frame. Another conventional IC packaging process, mostly we are using it at the wafer level or panel level process. It's compression molding. Like here, there is a very large wafer, and we mount several chips on the wafer. Then we put the powder or liquid molding compound on it, and move the moving mold to compress it. And this is the so-called compression molding. Using the numerical simulation, we can predict the potential void location to avoid it, and we can also got all of the physical variable by the result, like pressure, temperature, shear stress, the conversion, and the warpage. By the FSI computation, we can also predict the displacement of the die, because with the compression molding process, the shear stress is very large for this field. And we can also compare the shear stress and the bonding strength at different temperature and different time to make sure the bonding strength is enough to against the shear stress. About the advanced packaging process, mostly they are under field type process. Currently, the people use the triplet design is very popular, and people would like to put multiple chips on the same package, and the gap under the chip is very small. Therefore, we need to use the underfield to encapsulate the gap. This kind of process, like capillary underfield, dotting and potting, this kind of process. And these are the governing equations. The very important part is about the conversion balance. And the capillary underfield the flow field are driven by the surface tension. Therefore, we need to do the very accurate measurement of the surface tension and contact angle, especially the different geometry. We need to get all the data to meet our different models. Here we can see we can solve the very high resolution free surface shape to get the accurate surface tension. But with the IC devices become smaller and smaller, and the number of devices are larger and larger. Therefore, to keep this kind of high resolution and affordable computational time is become impossible. Therefore, we are trying to introduce the equivalent model. We call it equivalent bump group model. This kind of model, we are deal with this these areas with solder bumps as the porous media, and find the weighting factor to use to simulate the capillary pressure with the different bump density. And these are the formulations. I skip this. And here is a verification by a very simple case. You can see here we use a very high resolution mesh to meet the boundary. We call it detail model. And this is the equivalent model. And by detail model, we need 2.8 million elements, and here we only need 17,000 elements. By the comparison of the experience data and detail model and the equivalent model, you can see we have very good agreement of them. And this is another application. We complete this test with a couple cooperation units. Here we use a glass die to try to do the experiment. And this is the dispensing path. This is first pass, second pass, third pass, fourth pass, and the fifth and sixth. Each pass we use 70 seconds for the duration. And this is cross section, and this is the comparison of the reality and our simulation. And you can see the 70 seconds may be too long. We don't need this long duration, actually. By the simulation result, we can also find the conclusion like that. And after we compare the different passes and the reality, we can find that if we are doing this simulation, we can find we need only 35 seconds for duration of the first pass, and after all the whole process, we can save around 50% of the duration of the cycle time. Since I have only 10 minutes to this speech, so allow me to end here. Thank you very much.
Well, today I'm going to introduce some of my recent work on the stabilized Galerkin Meshfree formulation for advection dominated flows, and how I use the concept of Meshfree to integrate into the machine learning formulations to enhance its learning ability. So before I proceed, I just want to dive into the main thing. I just want to briefly introduce, if you don't know me, I work on Meshfree methods, computational mechanics, for extreme event problems, as shown here. These are my recent demo, recent simulation results. And also recently using the neural network enhancement to speed up the finite element and do homogenization for multi-scale modeling, and also including using a neural network machine learning to enhance Meshfree method, as shown in this speech. So you can see that I mostly work on Lagrangian mechanics, Lagrangian solid mechanics, but why I choose Eulerian advection as my research topic in here. And the reason is I want to challenge one concept is that you mostly see Meshfree methods modeling fluid flow like this, because in Lagrangian mechanics make use of its Meshfree property, but it doesn't mean that you cannot use it for Eulerian type of simulation that involve advection. And advection is a very important phenomenon for shock wave, for turbulence. So I want to show that Meshfree can also do that, and because most of you may use just finite volume, finite element, IGA to do that. But I will show you that I can improve the performance of the Meshfree method in Eulerian mechanics to modeling advection, and also to show that I can use that concept to develop new machine learning methods inspired by Meshfree. So I'll use the standard advection diffusion equation to demonstrate the idea, although the formulation can be extended to Navier-Stokes equation, which I already done. This is a strong form of the problem, where LU is the flux divergence operator that including the advection and diffusion flux. And by integration by parts standard procedure, you get the Galerkin weak form as shown here. But it is, notorious or very well known that the traditional problem of Galerkin formulation suffers from the numerical instability, that you will see strong oscillation and numerical artifact near the boundary, especially when you face a high factor number, meaning the advection is really, really strong. So, there's a well-known method by, the big name Tom Hughes, the variation multi-scale methods. You can use that to stabilize the results, and also for boundary condition, you can use weakly imposed boundary condition by Yuri Baslov and Tom Hughes again to solve the problem. The idea is they can introduce the stringline upwinding, SUPG, well-known SUPG formulation, and also niche-like formulation to impose compatibility, regularization on the inflow, outflow, and also introduce additional coercivity to enhance this solution stability. And here we choose Meshfree reproducing kernel approximation due to the advantage that Chen had mentioned before, the control of local smoothness, the order of completeness, etc. And because of each Meshfree method, we usually adopt with nodal quadrature. But the methodology that I show next following on does not restrict to Meshfree. You can do that for IGA, for FEM as well, as long as you are using low order quadrature. And here I'll show two figures about using the above schemes that on simple 1D advection diffusion equation. This will be the convergence plot you will obtain. The colorful scheme curves are from nodal integration. You will get only rate of 1, although you're using linear approximation. And unless you are using high order Gauss integration, then you can get better convergence, desired convergence rate, but that will be cumbersome, of course. And the other issue will be the instability, that under high factor number, like this one is the boundary layer problem,
in 1D, you'll see the nodal integration shows these unstable modes. Right? You don't see that modes really strong in diffusion case, like Stokes problem or Poisson equation. But when you have advection diffusion, you have high pattern number, you see this strong oscillation. So in order to address that, I basically borrow this idea from JS' earlier work. One is called variational consistent integration. The other is called NSNI, which is a gradient-based stabilization. So the first one, the accuracy is due to the inability of approximation, especially for the test function, to reproduce Galerkin exactness in the variational equation of advection term, especially for advection term. So the idea here is I assume my solution that the trial function is a linear field and with specific test function and substitute into the weak form of the advection equation. For the diffusion part, if you check the diffusion part, you'll find out that the test function needs to satisfy actually the divergence theory. Okay, so that will cause that is actually called a linear constraint in the VC paper. But for the advection part, the tricky is you will find out that it actually requires the so-called quadratic condition in the VCI paper. So that means we need to have an extended condition to impose for the test function. Still, we can use so that the main point here is that even for linear approximation, you need a quadratic correction for the test function. And you can use the assumed gradient approach by imposing this residual, the error residual shown here, back into the test function to correct the error. Then you can recover the optimal convergence. The second enhancement you can do is by using the gradient type stabilization by introducing the high order Taylor expansion on the test function and trial function. And the key here, what I did here is to introduce that to the VMS term, the variable scale term, instead of the advection term, because first you will violate the VC2 condition, this one, because if you simply do straightforward Taylor expansion. The second thing is advection term is the non-self-adjoint operator, and the high order terms put on it, maybe you can imagine it's more like enhanced integration that will actually show a little bit more oscillation from the numerical observation or in our inner testing. So we'll actually do that for the VMS term to obtain more stabilization. And for the detail, you can check my paper in recent CMME paper recently published. So here are the results. You can show here that you can see no matter for the nodal integration and the Gaussian integration, you can say I show the rate of convergence of 2 for regular discretization, regular and irregular discretization. And also, of course, nodal integration shows much better computational efficiency rather than the Gaussian integration. You can use this one for your finite volume method as well to enhance that. And also it can enhance the transient problem, of course. You can see those spurious waves are gone for these cone advection cone rotating problem. So that's from Meshfree. So I have shown some method to correct the Meshfree formulation for advection. So I want to dive into the machine learning. Okay, so machine learning is I have to mention this famous work by Professor Kardianakis from Brown, the famous physics-informed neural networks. So by formulating the least square like energy functional, and to minimize it through the penalty formulation to impose this is a multitask problem, so we have to introduce penalty parameter to impose the constraint. We can solve the problem in a strong form sense, and since physics-informed network, it's actually more like a Meshfree method. You don't need the discretization. All you need to do is to choose different sampling points, then formulate the physical laws in the least square type by penalty method and optimize it. You can use TensorFlow, you can use PyTorch. And but you will find the problem is that this, the penalty parameter will be tricky in the advection diffusion problem, because if you choose large penalty parameter, you get yield condition. If you choose too low, you cannot impose it. And also, we found out that the boundary condition, the inflow and outflow, actually need different regularization. That will become the issue in modeling. If you're really in modeling the fluid problem, you'll find out that not all the schemes that really converge. So to enhance it, I actually revisit the two main famous schemes by Hughes and by Hughes for the VMS and WBC, the weakly imposed boundary condition.
The idea is since although I use least square type functional, I can design a least square functional that is similar, for example, to the weakly imposed boundary condition to impose coercivity, for example, and to impose the different regularization on the inflow and outflow boundary. And actually, for the formulation shown here, if you take a variation, it will degenerate to the WBC formulation. Okay, so this is for the boundary, and for the non-convergent or learning ability issue, what I did here is, although I use least square, I can still do multi-scale composition. You can do something like what Professor JS did, to use RK for the core scale, to use neural network for the fine scale that derive the scheme. But here I didn't do that, I just used neural network for everything. So you can substitute it into the least square formulation, and then do variation to derive the fine scale solution, what it looks like, and eventually this will be the final equation. Right? You can see that this one actually comes from the least square loss of the momentum balance equation, and this actually gives you what additional term that is looks like this, where LUH minus S is the strong form loss, and you take advection operator on it. So this is similar actually to the so-called soft lobe training, and I think it's Sunwei-Shin's paper, recent paper, in the crystal plasticity to enhance the learning ability, or more recent paper by Professor Kardianakis for the so-called gradient PINN adding gradient term. But for their methods, they don't have specific definition on these parameter, regularization parameter C. But here, because of this procedure, I can actually derive the form of C. Okay, and actually I only need C in the solution. C is 10 to the power of -4. That's enough for my purpose to model the problem. So show this one static using Monte Carlo integration. This is one kind of nodal integration. The gray and light blue curve are by conventional penalty methods, and neural network strong for enforcement method. You can see that solution even diverge or not satisfy that good. And the blue and red curve are the proposed scheme. You can see that with VMS you get better learning ability. And also this is the famous advection skew problem. You will see that on the diffusion limit, even penalty method, I didn't choose penalty, I already regularized it. It does not satisfy the boundary condition very well. The proposed scheme, two schemes are match the FEN solution. FEN I use 100 by 100. This one I only use 10 by 10 neural network sampling points. You can see the accuracy is amazing. Also, here you can see that at advection limit, you will see penalty method directly diverge. And my solution, WBC and WBC plus VMS, is very close to FEN. WBC shows a little bit overshoot and undershoot behavior that VMS can cure that, but from 2D figure, we can see I cannot show that. And this is my recent progress to do shock modeling for Berger's equation. You can see that I apply the method to the Berger's equation, nonlinear transient. Probably you can see that all the shock wave refraction and shock wave and this shock nodes are captured. So I think due to the time issue, maybe I'll just quickly conclude. So I provide Meshfree correction to model advection, and I show that we can, for people, I usually used to work on conventional Meshfree numerical methods, but now even machine learning is a popular field. I'm not afraid of that. I could actually, some of the method, the idea that from the numerical method, they are those mathematicians when they develop the method that can actually use in machine learning. That's what I'm trying to say. And we can get better convergence, robust simulation results, and outstanding efficiency. So with that, I will conclude my talk. Thank you.
期待更多年轻的朋友加入学会。那学生特别便宜现在加入有优待，所以欢迎学生在外面加入。那如果你没有钱付钱找你的指导教授。那我们再一次谢谢这一层这个非常精彩的演讲，还有我们4位讲者谢谢。那我们今天活动就到这边，那谢谢大家今天的参与，谢谢。